Welcome back. So this is part two of music generation with the implementation of RNN neural network. In the last section, I discussed how to create data set for music generation from music, and today we'll discuss about how to create batches of batches of data from the data set, and then use this batch for our training. So just to recap, the music generation or a music data set usually have looks something like this, and we were able to take each and every character and map it to a number, right? So that it can be used for our PyTorch model training purpose. Okay, so now we have a vectorized string, which is basically an array of vectorized song that will be used for our training model. To give you an idea, we can first so this is how we get the end of a vectorized song string. So just a vectorized song shape 0 minus 1. So that gives me the total length of the string. And then we can do this two ways. First, we can randomly choose a starting batch of starting string, and we can generate few randomly chosen indices for the starting purpose. And later on, I will show you how we can use a sequential batch so that we don't miss any part of the training data set. So going over this get batch, this is an example of randomly using data. So IDX, we generate a random data. So before I go into the get batch method, I wanted to show you an example. So notice here we have a X and a Y. So how would my X and Y batch Y look like? Right? So what is my training and what am I what is my level, right? What is my X or what is my Y? So if you notice here, I have generated two batches, and the first batch is what I'm printing over here, has a sequence length of 10. So both X and Y has a sequence length of 10, but it has, but the Y actually begins one element after the X's batch size or X's batch. So what I mean by that is you have 1, 26, 32, and notice here the Y starts from 26, 32, and it predicts the next sequence 8. So both the sequence length remains the same, but there is an sequence or I plus 1. So it starts from, if X starts from 1, then Y starts from I plus 1. And you have to keep the sequence length same all the time. So this is the length of the string, randomly choosing, so we are passing the batch size and randomly choosing the starting index for the training batch. And then I'm constructing the input batch. So input batch is I to I plus sequence length for I in IDX. So the number of batches I want to, or the starting index. And the output batch also belongs to IDX, but it starts from I plus 1, right? So finally, we get the input batch and the output batch and convert it to X batch and Y batch. Okay, so this is just a simple testing purpose. So our torch size is 2, so because I passed the batch size of 2 and the sequence length is 10. Okay, now I made a small modification to this get batch size or get batches, and this is get sequential batches. So the difference between these two is basically, so the difference is effectively generate sequential batches from a large array of vectorized songs for training a model, particularly for tasks requiring the maintenance of sequence or order. So like a time series prediction or certain types of text processing or music generation, this is usually the way to go about. So for sequence purpose, we first need to calculate how many complete batches we can form from the data set, and we will trim out the data that or discard the excess data at the end, because we don't want to keep any batch incomplete. So here we calculate the number of batches that can be created. Then we are trimming, take only enough character to make a full batch. So we are trying to figure out the trimmed length. And then we are modifying our vectorized song to the trimmed length. And then reshape the batch size and reshape it according to batch size. And then finally, we are creating this, and finally using the for loop, we are creating all the data. So we iterate over the reshaped data, stepping by sequence length each time to create input and output sequences. So the input batch consists of subsequences, subsequences extracting starting from the index I, and the output batch starts from, as I mentioned, in next index I plus 1 to predict the next element in the sequence. This setup is typical for many prediction tasks where the model runs to predict the next item in the sequence. Okay, so just this modification of iterating through the batches, and then you can do some tests, and this is what my batches look like. It's not good idea to print the batches, it's just, but I just, for this purpose, I wanted to show how the batches look like, but otherwise it's not necessary. Okay, now we come to our main section, which is how do we define our model. Right? So for this model, we'll be using LSTM architecture. So where we use a state vector. So state vector are nothing. It keeps an or keeps a knowledge of the input sequences. It sequences from the past to the future, or past to the present. So t minus 1, t plus 1, and things like that, right? So it's a temporal relation between the consecutive characters. The final output of the LSTM is then fed to a fully connected linear layer, where we will output a softmax over each character in the vocabulary and then sample from that distribution to predict the next character. Okay, so just going over this again. So this is my input character, and it is converted to an embedding. So we use an input layer. So and convert it into an embedding layer. So we use the RNN.embedding from PyTorch actually. And then finally, then there is a character embedding. We use the LSTMs, and these LSTMs keep a idea or keep a tab on the state. And then we output the LSTM. So then the LSTM outputs are passed to a dense layer or NN linear layer. And then based on the probability value, we can predict the next sequence. Okay. So let me discuss about how this LSTM model is generated. So we'll start with the initialization method, init method, which takes in the vocab size, embedding dimension, and the hidden size. So so we do assign the hidden size to the hidden size embedding layer. We use the NN.embedding, which takes in the vocab size and the embedding dimension, each size of each embedding vector. So each word or character from the vocabulary will be transformed into an embedding of this size. So embedding dimension means that if you have like 256, so each character would be represented by a vector of size 256. And then we are defining our LSTM layer or LSTM architecture, which takes in the embedding dimension, then hidden dimension, and Yeah, and these are kept as the number of layers is 1 and batch first to just the default setting. So the LSTM layer is where the actual recurrent computation happens. It takes the embedding of words as input and processes the sequence one element at a time, maintaining information in its hidden state across the time steps. So it goes over, so the hidden steps are the information that are actually stored across all the time steps from the past to the present sequence. And then we define the fully connected layer, which takes in the hidden size and the vocab size. And this fully connected layer will give me the logic to which I can pass a softmax, and then I get the values, logic values. So it typically maps the output of the LSTM layer to the size of the vocabulary. So the vocabulary, so it will map it to the vocabulary size, and the character, which has the maximum probability, will be the next sequence prediction for our RNN model, basically. So what do you mean by why do you use the init hidden? So this method initializes the hidden state and the self state of LSTM to 0. So the initialization is done to 0. Now let's define the forward method. So the forward method defines how the model processes input and moves to the data. So the parameter is X, the input sequence of word indices. And state, that is optional. The initial state of LSTM layer, if it is not provided, it will be initialized through init hidden. And then return state, boolean that indicates whether the method should return the output along with the new hidden state. Okay, so return state is false, so it's not going to return the return the state along with the hidden output. So just sequentially putting everything, x equals to self embedding, then self.init hidden, then we call the self.lstm, the LSTM model, and then the out fully connected layer, and then we return the out, and if the return state is set to true, then you also set out the out and state will return out and state. Okay, so now we have now we can initialize the model. So vocab size is the length of the entire vocabulary that we have for this vectorized string or vectorized song. Embedding dimension is 256. So each of these vocab will be actually defined by 256 vector size. Then the hidden size that the LSTM model takes is 1024. Batch size is 8. We also have to mention that the device is screwed up, and then just create the model and pass the correct value, and we have to mention to device. Okay. Now this is important to define the loss. So we also have to compute the loss between the predicted and the actual value, of course. So we will define this with a cross entropy, NN cross entropy, instantiate this function from PyTorch, and then I'm defining the compute loss. So this batched levels and are the levels or the y value, y batch basically. We flatten it out, and the batch logics are the predicted values that we get from the model. We also flatten this and then take the difference, the loss difference to cross entropy. So we compute the cross entropy drop, and then we return the loss. Okay. So now again, this training step, I first introduce the get batch, and then I'll be modifying it to get a sequential batch method. So first, in the training state, we have defined the model. The model has already been defined. It's defined again. Model to device, that has also been done before. Here we use a blank string for a blank list to capture all our loss values, and you can have any optimizer, but I used Adam optimizer with a learning rate of 0.01. So these are all trainable parameters that I will discuss in my later videos, how you can train these parameters to width and biases. The clear TQDM instance if it exists for epoch in range 10. So you put the model in the training mode and then grab a batch and propagate it through the network. So we grab the batch vectorized song and we mentioned the sequence 100, sequence size 100, and then I mentioned a batch size of 16. Okay, and convert. So we are converting into the PyTorch tensors and putting it to the device. So here's the so these are the steps you should follow when you're doing it. Of course, doing a training. So we usually would put this to zero gradient for each and every step. Do the forward pass and y hat. Then we are computing the y batch and y hat loss, and then back propagate it to update our width. And the updated width or model is updated using optimizer.step. Okay, and then just printing the loss for each and every epoch, or you can also append it to the history or like the blank or to the list, history list. Okay. So now, so this was for only randomly picking a batch. Now let's, so everything remains the same. Now here we make the change of getting it from the get sequential batch, right? So we will be using all the data, and then we will go over batches of batches of data at a time. So here X batch, Y batch in okay. Sorry. So X batch and Y batch, we go iterate through the get sequential batches, and then sequence length and batch size was mentioned earlier. We can just use that, and then put it to the device. So the X batch and Y batch, and these remains the same: zero gradient, forward pass, compute the loss, backward pass, and then update the parameters. Here, I use a total loss because I'm keeping a track of all the loss that is happening within the batch for one epoch. So you can mention this total loss at the beginning of the epoch and kind of a batch count because I'm trying to make a average of the loss. Okay, so calculate the average loss, and then I'm also tracking it to my history, like also declare the history blank list in the beginning, and I'm tracking this to my history. Okay, so this is quite simple, like just a few modifications over there. So I can track my history equals to train step now. And as you can see, this is going over the epochs and it's training the model, and this is my average loss. So after your epoch or your training is completed, it's been running for 20 minutes now, and I think it will take some more time. So you can plot the history with epoch versus loss. However, I can definitely say that with a small number of training epochs like 10, it's not going to be, the loss is not going to reach really low. So you need to keep training this model for at least 100 epochs. And also, it's a good idea now to create an evaluation or a validation set and evaluate how good it is doing on the validation set. So I'll be discussing this in my next video.